Hi folks, we're going to take a look at number 10 from page 128. So they give us this position function, and there's a whole series of questions that they ask us to solve. So part A asks us to calculate the object's velocity and acceleration. So of course we think of the velocity is just the derivative of the position function, because it's just the rate of change of position. So I'm going to take the derivative here. Now, I can do this by using the product rule, but I think it's pretty easy to just distribute this and perhaps use the derivatives of powers of t instead. All right, so let's go ahead and do this. So I'll start by, okay, so notice here when I write the notation, my variable, my input variable is t and not x, so that's why I'd write d dt. Okay, so this is going to be 7 t to the 5 over 2, and then minus, well, 5 over 2 plus 2 over 2, because it's t to the 1, is t to the 7 over 2. And so now I can take the derivative very easily. So this is going to be 5 over 2 times 7, so this is going to be 35 over 2 t to the, well, 5 over 2 minus 2 over 2, so minus 1 is just 3 over 2, okay, and then minus 7 over 2 t to the, and 7 over 2 minus 2 over 2 is 5 over 2. All right, so here's our velocity, and now we can find the acceleration. Okay, and the acceleration, of course, is just the derivative of the velocity function. Okay, so it's already in a nice format here. So here, 3 over 2 times 35 over 2. So 3 times 35 is 105, and 2 times 2 is 4. So it's going to be t to the, and subtract 1, or 2 over 2. It's just going to be 1/2. And then minus, so 7 over 2 times 5 over 2 is going to be 35 over 4. And that's going to be t to the 5 over 2 minus 1 is just going to be 3 over 2. All right. So here are my two functions. And so now we're going to go to part B. So this was part A. And part B says, after how many seconds does the object stop? Okay. So what does it mean to be stopped? Well, it means that the velocity is going to be equal to 0. Okay, so in other words, let's take our velocity function, 35 over 2 t to the 3 halves minus 7 over 2 t to the 5 over 2 needs to be equal to 0. Okay, now in order to solve this, what I'm going to do is I'm going to use a slightly clever factoring trick. So first of all, here I see I can factor out a 7 over 2. Okay. And we'll see what's left over. But here I notice that I've got these rational exponents, so I'm just going to factor out the lower of the two, because if you look at these two exponents, they differ by 1. So let's see what happens when I take out the lower one, 3 over 2, and let's see what we're left with. So here I took out a 7 over 2, so the only thing I'm left with here is 5. Okay, I've taken out the 3 over 2 minus, so the 7 over 2 is gone. And let's see what happens when I divide out t to the 3 over 2 from t to the 5 over 2. So I'm doing a division, so I'd be subtracting the exponents. So 5 over 2 minus 3 over 2 is just 2 over 2, 1. So I'm just left with t. Okay, and we see how that makes it quite easy. Now to determine when this is equal to 0. So clearly it's equal to 0 at 0, okay? So that would be at the beginning of the experiment. So I think what we're looking for here is the second time when it reaches 0, and that is just going to happen at t equals 5 seconds. All right, there you go. So by doing some nice clever factoring, we were able to solve this very easily. So we'll go to part C. And part C says, when does the motion of the object change direction? Now, we might be tempted to just say, well, it must have stopped and then come back the other direction. But of course, what could be happening is the function could sort of instantaneously stop and then start up in the same direction. So in other words, what we have to show is that the velocity changes sign. Now, this is the only place where the velocity is equal to 0, so it's the only place where it could change sign. Okay, so what I need to do is I just need to check if it changes sign. So again, now we're talking about the velocity. does it change sign as we go from before 5 to after 5? Okay. And of course, we're going to co-opt everything we did in advanced functions, and we realize we can do that by just inputting one number in each of these intervals. All right. So what I'm going to do here is I have the velocity, but I'm going to look at the factored form of the velocity. Okay, because I think it's going to be a lot easier. So let's say I put in 1. Well, this is just going to be positive, and when I hear what I have, I've got 5 minus 1 is 4. So the whole thing is going to be a positive number. Whereas if I put something greater than 5, say 6, again, this part is just going to be positive, but when I input here, I get 5 minus 6 is negative, so I know that it's going to be negative. Okay, so that means that this object must have been moving towards the right, positive velocity, stopped instantaneous at 5, and then started moving to the left, and that's shown by the negative velocity. So again, the answer is at t equals 5 seconds. But had you just given me that answer, that would not be enough, because it's very possible that the object stops and then starts moving in the same direction. All right, so let's take a look at D. Okay, I'll do it up here so I can access the functions. So D asks, when is the acceleration positive? All right, so now I'm going to be working with the acceleration function. But again, if I want to determine the sign of a function, I'm going to want to find the zeros. Okay, and I'm going to do that by, again, some clever factoring. So here, the first thing I want to do is I want to take my acceleration function and determine where it's equal to 0. And then from there, I can use that to determine the sign of the acceleration. So I'm going to do something very similar to what I did before. So I see I have a 1 over 4 that's common to both. And here, these two things are both divisible by 35. So I'm going to factor out a 35 over 4. And then same thing here, I'm going to factor out the lower exponent of t, and let's see what we're left with. So here I'm just left with, well, 105 divided by 35 is just 3. Okay, that's gone, minus the 35 over 4 is gone, and when I divide t to the 3 halves by t to the 1 half, again, I'm just going to get t. So this is going to make solving this very easy. So clearly it's equal to 0 at 0, but that's the start of the experiment. The next time it's equal to 0 is at t equals 3. Okay, so now when I'm testing for my signs, now again, notice how I only start at 0 because we're not going to be dealing with negative time. So the only place where it could change sign is at 3. So this is where I'm going to test. So again, if we put t equals 1, this is just going to be positive. 3 minus 1 is also positive. Whereas if I put in t equals 4, again, this portion is positive, but I'm going to be multiplying now by a negative number. Okay, so here we can see that a of t is greater than 0 on, and what's my interval? From 0 seconds to 3 seconds. Okay. So finally, the last question is, when does the object return to its original position? Okay, so we're kind of coming back and going to the position function again. So again, being at the original position, we first have to determine what the original position was. So first I'm going to have to determine what s at 0 is, because at time 0 would be where it started from. But what is s at 0? I'm not going to bother putting it in. Clearly, it's just going to be equal to 0, because that's equal to 7, and this is just going to be equal to 0. 0 times 7 is 0. So in other words, I have to determine when is s at t going to be equal to 0 again. But this is actually going to be quite nice, because it's already in factored form for me. Okay, so I have t to the 5 over 2 times 7 minus t equals 0. So we already know that at time 0, it's going to be equal to 0. When's the next time it's going to be equal to 0? At t equals 7 seconds. All right. So this answers all the questions. Let's just do a quick recap. So we have this position function. We were able to, fairly easily find the velocity and acceleration by taking derivatives. Notice here how I use the trick of, distributing it up first instead of using the product rule. Okay, but then in order to determine the zeros, which I needed because I either needed the zeros or to help determine the sign of the function, I use this trick of factoring out, first of all, a constant, but also the lowest power of my variable, and that gave me, once I factor that out, gave me integer powers. In fact, not just integer powers, but power of 1 for t, which means solving much, much easier. All right, that's it for this one.